So we can use electronegativity values, which are found on the table, to determine whether a bond is polar or not. And you will be expected to identify whether a bond is polar or not. So the equation is here on the slide, and it's expressed by this Greek letter delta, which stands for change. Capital E, capital N stands for electronegativity, and A and B refer to the two atoms involved in the bond. So the difference in electronegativity between the two atoms allows you to determine whether that bond is polar or not, and we'll look at that criteria in just a minute. Here on the slide we see a graphic for a molecular model of water, and the bond between oxygen and hydrogen is polar. We'll see that in just a minute. Oxygen has a electronegativity of 3.5, hydrogen has one of 2.1, and the difference is 1.4. When you're figuring out the difference, you're just looking for the absolute value. So you always subtract this smaller value from the larger value. So this electronegativity difference of 1.4, we'll see, means this is a polar bond. Now, because water is a bent molecule, it is also a polar molecule. Just because a molecule has polar bonds doesn't mean that the molecule will be polar, and that's beyond the scope of this course. But if water was linear, it would not be polar. So the fact that it's bent is definitely important. Now, I also want to point out that because oxygen has the higher electronegativity value of 3.5 compared to 2.1, it has the partial negative charge, whereas hydrogen has the partial positive charge. So how would we know that this difference of 1.4 means the bond is polar? Well, we're going to use these rules that are found in your textbook. And if the difference in electronegativity is less than 0.5, then that is a non-polar covalent bond. If the difference in electronegativity is 0.5 and up to 2, then the bond is polar covalent, and the atom with the higher electronegativity has the partial negative, and the atom with the lower electronegativity has the partial positive. If the difference in electronegativity is 2 or greater, then the bond is considered to be ionic. Now, there's a little caveat here in Rule 4, because metals kind of muck up the waters, if you will. And if we are looking at a bond between a metal and a nonmetal, the electronegativity difference of 1.6 is enough for that to be considered to be ionic. So as you're looking at these differences in electronegativities, pay special attention to whether the atom is a metal or not, because if it's a metal, then a difference of 1.6 is enough to assign it a class of ionic. So on this slide, we see there is actually a spectrum between equally shared electrons in the nonpolar bond, unequally shared electrons in the polar covalent bond, and then complete transfer of electrons from the metal to the nonmetal in an ionic bond.